So, from chapter 1, chapter 2, chapter 7. So, giving all the figuring out, but some of that will be covered second class next semester. Okay. Fortunately, what we're going to see here doesn't rely on any of that. Okay, so there's a few, so far, chapter 2 was about error analysis for problems in general. The rest of the semester, we're focusing on a few specific problems that we want to find approximate solutions to. What we're concerned with first in this chapter is approximating the given function f of x by a polynomial. I don't remember if I covered piecewise polynomials. Oh, I do not. Probably because I don't like that topic. Yes, you get to do that at this level. But I gotta cover that. No, I'm not going to. Okay, I've also done it in classes like Cal 3, but okay. So approximating function by polynomial. And then after that, we'll start with chapter 9 for approximating derivatives and integrals, for which polynomial approximation is useful. And then the last chapter of the semester, chapter 10, will be about finding roots of a nonlinear equation, solving n equals 0. Okay. So all the concepts we've seen so far about error analysis then be applied to these particular problems. Okay, so a problem that we're focusing on now is this. That we're given n plus 1 points in the plane, so x values, x coordinates and y coordinates. And the goal is to come up with a polynomial of degree n that passes through each of these points. So in other words, it has to satisfy these conditions. The polynomial evaluated at each x value is equal to the corresponding y value. And I need to make it clear that this applies for I going from 1 to n. So n plus 1 conditions in all. So we refer to Pn of x as the interpolating polynomial of degree n for these points. Now, you can think of this as a generalization of a problem that you've long since known how to solve. And that is, given 2 points, what's the equation of a line that passes through them? So in that case, you find the slope and the y-intercept, or maybe you do point slope form. But now we're dealing with higher degrees. So if you have, so since 2 points determines a line, 3 points determines a quadratic or a parabola. 4 points determines a cubic, and so on. So that's why we have n plus 1 points determining the polynomial of degree n. So the degree is always 1 less than the number of points that you have. So for a polynomial of whatever degree, with however many points, how do we come up with this polynomial? So here's an example. So here's some given data. So I have points indexed to x0, x1, x2, x3. These are my x values. So -1, 0, 1, 2. They happen to be equally spaced in this example, but that's not necessary in general. In fact, it could be a bad idea in some cases. And then here are the corresponding y values. So since we have n equal 3, to go with points x, x0, x1, x2, x3. It's a cubic polynomial, so degree 3, that passes through these 4 points. So what we do, one way of obtaining a polynomial is we assume, because it's cubic, that it has this form. So this is the standard form of a polynomial called power form. So what's missing is we need to know values of these coefficients, A0, A1, A2, A3. So to figure out what these unknown coefficients must be, what we do is we substitute each of these x values into this equation. And that gives us this. So substituting x0 into here gives us this on the left side, and the result must be equal to y0. So I plug in each x value into a polynomial, I set it equal to the corresponding y value. So for this cubic polynomial, I have 4 equations corresponding to the 4 data points that I can solve to obtain these 4 unknowns, A0, A1, A2, A3. Now, this is a system of, not n plus 1 linear equations. Wow, there we go, on clock for 4 years. That's why I wrote these notes. In n plus 1 unknowns. Okay, sorry, I'm having a little freak out right now because the notes are kind of sort of based on the book, and if I said the same thing incorrectly in the book, that's gonna be unfortunate. So now, of course, I have to look. Doesn't necessarily play out that way. Okay. Looks like it's written differently in this case. So, nope, I did not do that. Okay. So, actually, I should mention now, on the subject of mistakes in the book. If you go to my web page, okay, well, you don't have to include the cat part. Okay. I have to move across. And my web page address is a syllabus anyway, but okay. So, so I have links on my web page for the both versions of textbook, MATLAB edition and Python edition. Julie edition still in the works, but progress is slow. And what you'll see if you scroll down, a long list of found mistakes. That's an embarrassingly long list. And the worst part about it is there's still several more mistakes that have been discovered since then, since this list was made, and I haven't added them to the list yet. That's one of the reasons why I'm doing the Julie edition, that please fix these. And I'm grateful, even if probably so, to all the students over the years who have found these mistakes. So, now, what is this mistake? Here's only the notes. All right, so we have this system of linear equations. So you can solve this using methods of like Math 326, row operation, Gaussian elimination, and all that junk. Now, it can be shown. I won't show it here, and you can thank me for not assigning the exploration about this. It can be shown that as long as the x values are distinct, that the matrix of the system is guaranteed to be invertible. In other words, it can be shown that the determinant of that matrix is non-zero. So right over here we have an approach to obtaining the coefficients and obtaining the interpolating polynomial. And in fact, this approach that I've shown you right here is what MATLAB uses to find the interpolating polynomial. And I think that function is discussed in the tutorial. Let me check. I have a list here in the tutorial of polynomial functions. Oh, but I don't have it in this list because it wasn't part of the tutorial. Okay, dang it. Okay. I will show it to you later. But there's a MATLAB function called polyfit. You give it x values, you give it a vector of x values, you give it a vector of y values, you give it a degree, like a maximum degree, and it will compute the interpolating polynomial for you. And in the case of n plus 1 points and finding the polynomial of degree n, it sets up this system of linear equations and solves it. Okay. And I should mention that the matrix involved is called a Vandermonde matrix. Right. So, because I think I can show you. Oh, I don't have it here. Sorry. Okay. Because you'll be seeing it in the some of the homework problems. I'm going to write out the matrix here. And it's good to show you all, if you have a system of equations written out, don't do this to me.
Something wrong with the notes?
Yeah. As I was typing, the program is hanging. And someone tells me it's going to go in, so you Mac users will appreciate this. I'm getting the rainbow colored pinwheel of death.
I don't appreciate what's going on.
Well, neither do I, but any Mac users would be familiar with that. And I'm feeling the program is not going to recover. I'll probably have to shut it down and restart it. Dang it.
I don't use a Mac.
Good then.
Okay. All right. I'm gonna go close this down. Hopefully, I didn't lose too much. But yeah, it's quite aggravating when that happens. Okay. Let's try this again. And hopefully, it won't freak out. Okay. Oh. Yeah, there was a little bit off, but not much. Okay. So.
What did you lose?
Just when I put some space in between here to start typing out the matrix. Okay. Let's try this again. Right. Hopefully it won't flip out.
tried to join the class online and it said WebEx isn't working.
Who's who?
Courtney.
Okay, I'm not sure what that means because we have several people attending online. And sure enough, the program is freaking out again. Okay,
That's no good.
alright, I may have to do this differently. Yeah, I think when I try to create this matrix environment, what it does is it processes it on the fly. And it might get confused in this case. So, I hope I won't have to give up on doing this, because I really do want to show you the matrix. Once it'll let me save the file as I go. Oh, nope, it won't. Okay, now it's letting me proceed. So, if you have a system of equations like this written out, you want to express it in matrix vector form to get the coefficients of the matrix, you take whatever numbers are multiplying your unknowns. The unknowns in this case are A0, A1, A2, A3. So the first column consists of whatever is multiplying A0, which in this case is all ones. So that's going to be the first column of the matrix. The second column matrix is whatever is multiplying A1, which is the x values, x0, x1, x2, x3. Third column is whatever is multiplying A2, which is x0 squared. You can start to see a pattern here. And finally, for the fourth and last column, x0 cubed. Okay. So now I've completed the first row, and then I'll just quickly duplicate this for the other rows. Okay, so I have x0, x1, x2, x3, and then squared. All right, so this is a matrix of this system. There's a function in MATLAB called Vander that actually generates this matrix given the x values. Right. So as I mentioned, MATLAB sets up this system of equations in this van der Waals matrix and solves it for the coefficients, and that's it. So you might think, well, that's all there is, right? I presented a problem computing a polynomial that passes through given points, and now we have a way of computing a polynomial, so isn't it Miller time? But no, we're actually just getting started. Okay, so this is actually a terrible approach. It's a straightforward approach to computing the coefficients of our unknown polynomial, but it's a terrible approach. And which makes it all the more flabbergasting that MATLAB actually uses it. I'm about to teach you about better ways to do it, and whatever. Here are the significant drawbacks of this approach. It's not efficient. So for generating a polynomial of degree n by solving this van der Waals system, it requires on the order of n cubed arithmetic operations. This is the same big O notation that we've been using from section 2.1. So what I'm saying by making the statement is that the number of arithmetic operations needed to solve this system can be bounded by a constant times n cubed for n sufficiently large, as n goes to infinity. So, And that's pretty expensive. Now, there are a lot of algorithms, the ones we'll see later on, that require this much work. However, what we'll see later in this chapter is that it's possible to compute the coefficients of a polynomial in order n squared operations. So if we can reduce the amount of work needed by a whole order of magnitude, then why not? That's one problem. It's slow. Also, it's not robust. So numerical algorithms, we like them to be accurate, we like them to be efficient, and we like them to be robust. And this approach fails on two of those three criteria. So again, using terminology from chapter 2, this matrix is ill-conditioned, especially when the x values are close together. So the coefficients that you obtain by solving this system might not be as accurate as they can be. So we're not going to consider this approach any further. Although I do give some homework problems about it, but I'm not going to talk about it anymore. Okay, are there any questions about this whole setup of solving the problem this way? It's not terribly interesting, honestly. So now we'll consider one other approach today called Lagrange Interpolation, something that at least some of the people in this room are already familiar with. So, as I mentioned earlier, the way that the polynomial was written before, which is what we're accustomed to, this form of polynomial, constant plus constant times x plus constant times x squared and so on, this is called power form. So expressing your polynomial in power form that leads to a system of equations may not be the best approach, but there are many ways you can represent a polynomial. So what we're going to use now is called Lagrange form. So same polynomial, because remember, I mentioned earlier that system, as awful as it is invertible. That means the interpolating polynomial is unique. So I'm going to show you, I've already shown you one way to compute it. We'll see two more. All three approaches will generate the same polynomial. But we can write that polynomial in different ways. So Lagrange form looks like this. It is a linear combination of what are called Lagrange polynomials, which I will define momentarily. But notice that the coefficients of this linear combination are just the y values. So in a way, it's the opposite of the approach of using a van der Waals matrix, because in the case of power form and solving a system of equations, the form of a polynomial is very simple. The coefficients are difficult to get because you have to solve that system. Here, it's the coefficients that are trivial. It's making these polynomials that take some work. So the Lagrange interpolation is the opposite in that sense. Okay. So now I need to tell you, what are these Lagrange polynomials? Lagrange polynomials, I need them to satisfy these conditions for all indices I. That if I plug in one of the x values, so xi, that means I'm going to evaluate each Lagrange polynomial at xi. And I need this summation to evaluate to yi. That's how the interpolating polynomial is defined. I plug in xi, I get the corresponding yi. Now the only way that this is guaranteed to happen regardless of what the x and y values are. I mean, we're assuming the x values are distinct, but otherwise, there's no limitations whatsoever on the x's and y's. I need this to be true, that these Lagrange polynomials must be equal to 0 at all of the x values, except for one of them, at which it'll be equal to 1. So that's why I index Lagrange polynomials, but okay, n is a degree. We're looking for an nth degree polynomial. And then this second index here, that indexes all Lagrange polynomials from 0 to n. So each Lagrange polynomial is associated with one of the x values. At its own x value, it must be 1. Otherwise, and the other given x values from your data must be 0. So by satisfying these properties, then this will happen. So now I just have to show you, bless you, how do we construct all of these polynomials that have these properties? So, going back to the example, I've given sample data. I'm looking for a cubic. I have 4 points. I'm looking for a cubic. So my interpolated polynomial now has this form: a linear combination of these 4 still unknown Lagrange polynomials. You're probably wondering, like, okay, Dr. Lambert, can you show us what these are already? Multiplied by each of the y values. I'm getting here, I promise. So, and the y values from earlier are 3 minus 4, 5 minus 6. Okay. So, so what are the conditions that these Lagrange polynomials have to satisfy? For each one of these, if I plug in the corresponding x value, I have to get 1. So if I plug in minus 1 into the first Lagrange polynomial, I'll get 1, because minus 1 is the first x value. But if I plug minus 1 into the other Lagrange polynomials, I have to get 0. And this continues for all of the x values. Here I'm plugging in x equals 0, x equals 1, and then x equals 2. So all of my x values. Questions so far? Okay, now, let's take a look at the first column here. So, the first equation in each row deals with L30. So that's one of the Lagrange polynomials. And we see that it must be equal to 0 when x is equal to 0, 1, or 2. When x is equal to minus 1, it must be equal to 1. So, here's a formula for it. Right here. I want this polynomial to be equal to 0 at 0, x equals 0, 1, or 2. Well, that's going to give me this factorization. 0, 1, and 2 are the 3 roots of this Lagrange polynomial. So this is my starting point. I just take those linear factors, x minus each of the points where I want it to be 0, multiply them all together. So if x is equal to any one of these, the whole thing will be 0. So this numerator is all I need to make sure that this polynomial is equal to 0 wherever I need it to be. But then, I have to make sure if I plug in x equal to minus 1, that I get 1. And if I do that with this numerator, I'm not going to get 1 necessarily. So what do? I go ahead and plug in x equal minus 1 into each of these linear factors, and I divide by it. So then, if I plug in x equal to -1, then the three linear factors I get up top are canceled by the linear factors down below, and I'll get 1. So that's how you make a Lagrange polynomial. And you can see the pattern, like for instance, if I do the second one. So now I'm looking here at the second equation in each row. When x is 0, I want it to be 1. When x is equal to -1, 1, or 2, I want 0. So I set these linear factors accordingly. And then I plug 0 into each of those linear factors and divide by it. And so that's how the process plays out in general. In fact, this right here, this is the general formula for Lagrange polynomials. Actually, I'm going to try to make this typeset that's a little more readable. Okay, yeah, that's better. Okay. So what we have here is Lagrange polynomial corresponding to xj is a product of x minus xi, where I is not equal to j. And then, so that ensures that this Lagrange polynomial is 0 wherever it needs to be 0, for all xi not equal to j, xj. And then, if I substitute x equal xj into each of these factors, that's what I put in the denominator to make sure that it's equal to 1 where it needs to be 1. So then you have the interpolated polynomial set up that way. And here's the MATLAB function for polynomial interpolation, how you use it. So polyfit. So you give it a vector of x values, you give it a vector of y values, and then the degree n. Now, for polynomial interpolation, like I've been showing you, the way you should set n is the length of x minus 1, because, like, for example, in this example here, 4 points, you get a degree 3 polynomial. And what it outputs is a vector of coefficients. So we saw in the tutorial how polynomials are normally represented in MATLAB. It's a row vector of coefficients ordered from highest degree to lowest. And that's what is returned by polyfit. It just uses that stupid Van der Waals matrix. Okay, question about how Lagrange interpolation is carried out. Okay. So I actually have a nice graph showing Lagrange polynomials. The cover of our textbook. If I make it a little bigger. Okay. Now, the black dashed curve is a polynomial that is designed to pass through the tops of all the cacti. See this, you have a blue dot here, a yellow dot here, green one that has cactus far in the background, and then this red circle, this cactus. It was quite a chore to explain to the poor artist at my publisher what I wanted. That had to review that. So
Poor artist at your publisher,
what?
the poor artist at your publisher.
Yeah, but they had some difficulty understanding what I wanted. We had to go a few iterations. Well, that reminds me. Okay, I think I might have it accessible. Oh, no, that's not what I want. Okay, that's actual cover, but. What did I have? Okay. I found another version. Oh, maybe this. I'm sorry, I know I'd seen it earlier. Ah, this is what I was looking for. Okay, this here, so my co-author, Amber Sumner, she had gone to Painting Book Twist, right here in Hattiesburg, and she painted this. Yeah. So then, so I sent it to my publisher and said, we want something like this. And first time around, they got some nice practice, but they got the curves all wrong, and then I had to like recreate it in MATLAB. Like this thing. Yeah. It was a bit of work. Okay, so now if I go back to picture. Okay, the solid curves, the blue, yellow, green, and red curves, are Lagrange polynomials for these x values, where you see the blue, yellow, green, and red dots. So this line right around here is the x-axis. So if you take the blue curve, for instance, okay, so that this first interpolation point is where it's equal to non-zero. It's not, now this is a scale Lagrange polynomial, so it's equal to the y value, this interpolation point. But then if I look at the x values where the other circles are, the blue polynomial is 0 here, here, and also here. Whereas the yellow polynomial is equal to 0 at the first point, the third, where the green is, and then the fourth one where the red is. But here is where it's non-zero. And then you have a green polynomial that's non-zero here, but it's 0 here, here, here. And finally, the red one is 0 at the first 3 points and non-zero at the fourth one. So, in other words, the black dash curve is equal to the sum of the blue, yellow, green, and red curves. But yeah, we first discussed this cover. We thought of doing something like this with treetops, and then Amber's like, "No, let's do cactus." Okay. So now it's my legacy. I did the cactus book. Okay. I guess some explorations, miracle analysis, you're lost in the desert, and it's kind of fitting. Okay. So that's what ground polynomials look like. Now, so Lagrange polynomials are an improvement on using solving system linear equations because it's more efficient. They perform only order n squared arithmetic operations instead of n cubed. But there's one problem though, is once you form the polynomials, if you leave them in Lagrange form, they're not so efficient to evaluate. Because if you have a polynomial in power form of degree n, it's possible to evaluate it in order n arithmetic operations. If you arrange it properly. We're going to see something about that later. But with Lagrange form, it takes order n squared work to evaluate at a particular x. And that's too much work. I mean, because it's already known that we can do better than that. So, there is a way around that called barycentric interpolation that works with Lagrange form. And notice the date on this development, 2004. And so it's pretty new. So in fact, when I submitted the proposal for this textbook to my publisher in 2015, and she sent it out to be reviewed by experts in the field, and I had like my notes put together as like an early draft, and they said that, oh, my content is kind of dated because they did not mention barycentric interpolation, which by that time had been around for a little over 10 years. And I was like, well, I didn't know about that, so oops. So I put it in. And actually, I know the guy who developed it. It's Nick Trefethen, who recently retired from Oxford. And actually, if I look him up, not just Googling him. Okay. This is the Mathematics Genealogy Project. It's a database of mathematicians and math professors and their students. So here you see the list of all of my PhD students so far.
Your PhD students?
Yes. Well, the most recent one, Dr. Wright, she's on our faculty now. Just started. Okay. Oh, and there's Amber. She was my fourth one. So now I want to check. I had two advisors because Joe retired and then Gene took over. So I look at his students.
So,
Okay, there I am, and then there's. Yeah, these are my academic siblings. Oh yeah, there's Trefethen right there. Yeah, he's my academic, much older academic brother. But what's more interesting, I know I'm wasting time, but I don't have too much left. If I follow the ancestry of my first advisor, and this could be something, for those of you who are taking history of math, maybe you can point out to your instructor. Okay.
hey, there's your name in the 2003 year.
Yeah, that's when I got my PhD. So so this is all his students. And actually, if I sort by chronological order, okay, well, I was one of the last. He passed away in 2007. But, okay. So if I follow the chain, and hopefully I get it right. Okay, so if I keep going, okay, yeah, we're on the right track. That's some notable names are going to pop up. Lipschitz, Lipschitz continuity is named after him. Dirichlet's and Dirichlet boundary conditions, that some of you might know about. And then Poisson, Fourier's and Fourier series. And Lagrange. Yeah, so I am the academic descendant of many generations of Lagrange.
Your descendant is who now? I'm sorry, your ancestor is who?
Yes, I am a descendant of one of the most prolific publishers of all time, Euler. Yeah.
Euler's method?
Yes,
Oh, the Euler's method.
that Euler. Yes, him.
You're the descendant of that person?
Academically, yes.
Academically?
Yeah, because I'm not genetically related to them that I know of. But yeah. So if you look at his PhD students and all the way down the list, you come to me. So actually, what was the question? Oh, Bernoulli, yeah, that's a pretty well-known name too. And Bernoulli advised Bernoulli. That's weird. Okay, and I can go back pretty far. I think sometime around the 1500s might die out, but wow. Oh, okay, this is where it ends. Okay. Anyhow, yes. So, all right. So now, Trefethen's innovation of barycentric interpolation on how to evaluate Lagrange polynomials more efficiently. So what you do is you compute these quantities that are called barycentric weights, and all they are is so each weight Wj is just 1 over xj minus xi all multiplied together for all other xi. Now, the nice thing is, you only have to compute these once. So this is independent of whatever x you might plug into the barycentric polynomial. Okay. So admittedly, this part's expensive. It requires order n squared operations. But because it's a pre-processing stage, that's okay. Whereas if you ordinary Lagrange form, this requires order n squared operations for every single x you plug into it. Here we're doing a lot of work up front. That'll save us later. Okay. So once we have these weights, then what happens? This gives me another way of writing the Lagrange polynomials. That I can say are equal to the weights over x minus xj times this monstrosity. This polynomial is a product of x minus all of the interpolation points. So this is the polynomial degree n plus 1, but then I'm dividing by x minus xj, so the whole thing is still degree n. But what's important here is every Lagrange polynomial has pi n of x as a common factor. Okay, so now, using this form of Lagrange polynomial, here's what I can do. So I have P n of x, which is equal to the y values times Lagrange polynomial. But as I mentioned, pi n of x is a common factor, so I can pull it out of the sum. Now this is for whatever function y equals f of x I have. But what if I use this same approach on just interpolating the function y equals 1? So now I have the same kind of equation, but I'll have 1 on the left side. And then instead of yj here, I just have 1. Now, I can divide this equation by this one. On the left side, I get exactly what I want, Pn of x. The pi n's cancel out. So that's the genius of this approach. And this is what I'm left with. So now, to evaluate my Lagrange interpolated polynomial at any x, I can just evaluate these summations. And this takes only order n operations for each one. Now, notice I have in the denominators x minus xj. So I'm thinking, oh, well, if you plug in x equals xj, then you're dividing by 0. But we never need to plug xj into this, because we know what this should be. It should be yj. So yeah, this formula should only be used for other x's outside of your data. That's what interpolation is for. Your polynomial passes through prescribed points, but you want to be able to evaluate it in between interpolation, as opposed to like if you choose the x outside of those points. That would be extrapolation. Don't do that. Well, there's very limited circumstances where it's a good idea, but this is definitely not one of them. Okay. Oh, that's the end. So this is how Lagrange interpolated polynomials can be evaluated efficiently. Now, there's still one difficulty with a little drawback with this approach, even with barycentric interpolation. That is, suppose you're interpolating at a certain set of points, and then you want to add on another point, like maybe you gather more data. You'd like to fit this additional point. Then you kind of have to start over. All the Lagrange polynomials have to be regenerated. So it's not an easy form to update. Next couple of classes I'll be talking about the third approach to interpolation, Newton interpolation, where you can do that. And, but it turns out that, okay, so you can see a total of 3 approaches to polynomial interpolation. In my research, I've used all 3. It just depends on the situation as to which one is the most advantageous. Okay, so this is one approach to solving the polynomial interpolation problem. Finding the polynomial that passes through given points. One thing that's nice about Lagrange interpolation, in particular, is it wants to understand the pattern of how the Lagrange polynomials are formed. Like if you're doing this on paper, you can just rattle them off. So it's like a nice party trick. Not really. Or it's stop being okay. Questions about any of this? Lagrange polynomials, Lagrange centric, or anything else for that matter? Homework problems? Conflict check questions?
I have a side question.
Okay.
Why Barry?
Why vary?
Yeah. Okay.
I should know that, but I don't. And when I think barycentric, I think of barycentric coordinates for a triangle. And it's possible there might be some connection to that, but. I guess I should probably look at the original paper, and maybe they give an explanation for that. Okay. Well, I guess that's it then. And now I can resume celebrating my birthday.
What now?
Happy birthday. Happy birthday.
Wait a minute, when's your birthday?
Today.
Happy birthday.
Thank you.